Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I will help get you started with Class 22 on analysis of variance, that's ANOVA, and assessing assumptions for analysis of variance. And we'll be applying the ANOVA and follow-up post-hoc pairwise comparisons to your data set. So I'll scroll down to Class 22. Here we are. And there's no RMD file here, so that means that this assignment is in your project file. I will open up RStudio and bring in my project file. And knit it to make sure that we're starting with, rename it. And then knit it. Make sure we're starting with the file that is working. And while that's running, let's take a look at the rubric for this assignment, as well as the previous year's example. So we'll take a look at the rubric here, and we'll look at the previous year's assignment here. Okay, so first the rubric. This is Class 22 on ANOVA. So I just did a find Class 22, and we're down here. And it looks like a lot of parts, and it is. There's a lot to do on this assignment. So first, you have to decide on two variables to use. First, choose a numeric response variable for the y-axis for the response, and then a categorical variable with 3 to 5 levels. If you had 6, that would be probably okay, but you can't have 2. You need at least 3 levels, and then specify the Anova hypothesis associated with the data file that you're working with. So here are the 8 parts. First, specify the Anova hypothesis, both in words and notation. Then plot the data in a way that is consistent with the hypothesis test. That gives you a way to compare the means and also assess the equal variance assumption. Next, we'll use the Anova function, AOV, to calculate the hypothesis test statistic and p-value. And we will then state the significance level, which typically is 0.05. I recommend you use 0.05. The test statistic that you got up here, and the p-value. Okay, so you get a point just for running that function. You get a second point for just reporting those values. That's pretty good. Then, based on your p-value and the significance level, you can state the conclusion in the context of the problem, either by rejecting or failing to reject the null hypothesis. Then we've got 2 parts for checking assumptions. The first is checking the normality assumption of the residuals, and also checking the assumption of equal variance between the groups. Now, I know that it is very likely that your data do not have normal residuals. For the point of this assignment, we are going to do our best, meaning we're going to check them and see if we meet model assumptions or not. If we don't, we're going to continue anyway and finish the assignment. If we fail to meet model assumptions, we will recognize that in fact this is not the correct test to use, the ANOVA, but we should use, or at least the ANOVA with these model assumptions, we should use an analysis of variance such as Kruskal-Wallis or something else that does not have these model assumptions. And that is something that we'll learn about in a coming week. Okay, finally, if you rejected the Anova null hypothesis, then perform pairwise comparisons using Tukey's on a significant difference and indicate which pairs of means are different. So all of these parts are parts that we've seen in the previous assignment. Now it's just up to you to apply them to your data set. I'm going to go over to the model assignment from a previous year to get started for myself. And down at week 9 is the Anova. And this version of it actually has a couple more steps that we're not going to follow. In particular, I start off by talking about the Cox Transformation, which is a way of taking the response variable and raising it to an exponent in such a way that you get residuals that are closer to normal. And that's a very common technique, but I think it's a little premature to introduce in our class, and maybe a little bit beyond the scope of Data Analysis 1. This is maybe a better topic for next semester. Anyway, so I'm going to skip some of the details from relating to the transforming of the y variable here. All right, but I will scroll down. So all this is Cox Transformation stuff up here, and I'm just skipping past it. I end up taking a square root of the total cigarettes smoked, and I'm not going to do that for this demonstration in our assignment. Okay, so we are down now at when we're going to start the Anova. Let's do a couple more things before we get started completely. The project file finished compiling, finished knitting, so I'm going to open this up in RStudio and search for class 22. Okay, so this is the assignment right out of our project file, so I can close the one from the website. And we're going to make sure that we get through each of these parts. So the first part is to identify the variables, and then using that specify the Anova hypothesis. The variables that I selected, go away. Okay, let's do that also. From here, let's do class 22. I searched for class 22 and it brought me down to the beginning of here. Okay, and I've got, let's just look at this over on the website instead. I've got subsections, right? So this is section 2.14. I've got subsections for each of these pieces. So we've got places to reduce writing and to interesting. So I have a transform and response variable to satisfy model assumptions. I think we're going to skip that part. Okay. Hypothesis and plot. Yes. Okay. Good. So hypothesis and plot are these first two. We're going to skip the transform the response variable. The third one is the Anova hypothesis test, and so on. Okay. I think we've got some good places to put some things. The hypothesis test will include the p-value and the conclusion. Then we're going to check our model assumptions and finally do the post hoc pairwise comparisons test. So we've got places to put everything. I will keep this up here where we can read them all, and let's get started. All right, so I'm going to actually remove, is that true? I'll make a comment here, not used. The transform the response variable. Okay, so for the hypothesis and the plot, I'm now going to go look at my example project, and I used total cigarettes smoked as the response variable and ethnicity as the categorical variable. So I've got 4 groups of ethnicities: Caucasian, African American, Native American, Asian, and Hispanic. And I'll just acknowledge that I'm using the ethnicities as they're defined in the NESARC dataset, and I'm just going to use them as is without thinking too carefully about that, unfortunately. And I've got my, I'm first defining some notation, which is helpful, and specifying the hypothesis test. or the hypotheses. I'm scrolling down for a moment to see I've got the plot there. Here I've got hypothesis test set up in words notation. And you can see actually I go through the steps of the hypothesis test as I've done previously from my model. Okay, so I'm actually going to do this maybe a little bit in a slightly different order than I have those parts defined here. Instead, I'm going to put all the hypothesis testing down here. I think that's either way is fine as long as it's sort of ordered in a certain, in a logical way. All right. So I'm going to save myself some typing since I'm stealing from myself effectively. And I'm going to find the actual code. Okay, so if I search for Anova Hypothesis test. Good. So I'm just going to grab stuff that I've written for myself before and put it into my document. Okay. And I'm going to have to change things because I'm not doing the square root of the response variable cigarette smoked. Okay, but at least this sort of gives me a place to start. All right, so let's run all the code from the top down to here. And that doesn't work because I didn't set the working directory. There's no one here to remind me. Okay, set the working directory. Let's try it again. Okay, so I'm starting by looking at a summary of the ethnicities just to get a sense of how many people there are. That's maybe, I sort of see that as maybe a second step. Maybe here it would be better. All right, so let mu sub j equal the population mean number of total cigarettes smoked for the 5 ethnicities. That looks right to me. Oh well. Identified in the data set. And the 5 are Caucasian, African American, Native American, Asian, and Hispanic, numbered j equals 1, 2, 3, 4, and 5 respectively. And I don't know why they're in this order. I think that they're in that order based on the code book. We wish to test whether all the means are equal. So H naught is that mu underscore 1 equals, C dots means center dots. We can take a look at that over here. Right here. C dots gives me those triple dots there. So it's mu1 equals, the triple dot stands for mu2, mu3, mu4 equals mu5. Okay, against the null hypothesis of not H naught, which means that at least one pair of means differ. Close parenthesis. And I've got a table of the ethnicities to compare is below. And then I plot the data in a way that compares the means. And I've got 95% confidence intervals of the mean. So this plot, all right, let's run a little bit now since it's finished. Here's my table of ethnicities, and I've got much larger sample sizes because I have not restricted the samples to young adults. It's now everyone, and I'm not going to, I don't have the square root total cigarettes smoked anymore, so I'm just using the original variable, and I'm just taking a quick peek. Total cigarettes smoked. Okay, let's run the plot and see what we've got. I haven't seen this plot yet. It's taking a long time because the samples are very large and I'm plotting all those points. A more efficient plot would probably be to do histograms instead. You can see a lot of right skewness in the data. The red diamonds are the means. It looks like Caucasians and Native Americans smoke more than African Americans, and Asians and Hispanics seem to smoke the least. That's just anecdotal from the plot. All right. So a way to get started on the hypotheses would be to, I don't know why that's happening. In the project file, there was a part, if I page up to the very top, under, oh, not the weak one. Okay, this is from our assignment. When I first started talking about hypothesis testing, right here I've got mechanics of a hypothesis test. Okay, and I recommend going to the R Markdown file and copying this text, and then you can delete the stuff you don't need and replace it with the stuff that you want. So that's what I've done. Set up the null and alternative hypotheses in words and notations. So in words, I've got the population mean, total cigarettes smoked, is different between ethnicities. So it's stated in terms of the alternative that there's a difference happening. In notation, and this is what I had written before, the means are all equal versus the means are not equal. That at least one pair of means differ. Let the significance level be equal to alpha is 0.05. Compute the test statistic. So here is the analysis of variance code. And I've got total cigarettes smoked as the response variable by ethnicity. And then I'm going to look at a summary. So let's run this and take a look. It's not every day you get an F statistic close to 500. So an F statistic consistent with the null hypothesis is close to 1. All right, so 500 is pretty far away. So we have a p-value that's basically equal to 0. It also has a note here that almost 300 observations were deleted due to missingness. So those are NAs associated with either missing ethnicity or missing total number of cigarettes smoked. All right, so I've computed that stuff there. Then this is pretty complicated right here, this piece of code. Let's try it down here. It's a way of getting the F statistic right here. So let me show you how to do this. When I fit the ANOVA, I got this ANOVA summary object. I'm going to give myself a little more space in the console. And if you look at the names of an object, you'll see sort of what's in there. And it's not really obvious where to look. There's nothing that says F statistic or even statistic. Without peeking above, I'll sort of show you what I would do. I put a $sign, I'd look at coefficients. Okay, so these are model coefficients that allow us to get the means for each of the groups. In Data Analysis 2, we'll learn how to interpret these. So that's not quite what we want. We've got effects usually isn't it. Terms is definitely not it. Okay, I need to go peek so I don't waste a lot of time. Oh, it's in the summary. Oh yeah, okay, good. So the ANOVA object that we get here is different than what we get when we look at the summary of that object. The summary produces some additional things. So if we look at the names of the summary, nope, I guess not. But I think this is a table. I did put a $sign and I pushed tab to try to autocomplete, but there's nothing there. How did I figure this out? I did unlist. So there is a list of objects in summary, and they have names. There's df1, which is the degrees of freedom for the numerator up top. Degrees of freedom 2, which is the 42,000, which is there. There's the sums of squares 1 and 2, which is 1 and 2. There's the mean square 1 and 2, which is this column. There's the f value 1, which is the first row for the f value. There is no f value 2, which is why it's NA. And then there's also the p value. Okay, so it looks like if I'm going to try one more thing. If I do a $sign and do brackets, gosh, is this even how to do it? Quotes f space value 1 and press enter, that's a null. But if I unlist it and call it that, I can get it. Okay, so if you unlist it, you get this list, and then in brackets, if you name f value 1, you can get that number. So it was a bit of work, but you can automate getting that value. And what I'm finally doing up here, and I usually do it slightly differently, I take that value and pass it to signif with 3 digits. So that the code, if I copy it down here, looks like this. So I had the unlist exactly like that, and then I pass that to 3 significant digits and get 496. So the sentence I wrote was the f statistic for the ANOVA is f equals 496 is what ends up getting computed. Compute the p-value. So I do the same thing. The p-value is the probability that greater than the f statistic, and that's going to be 0.00000. Let's just take a look and see what we get when we compute that. It may actually be numerically not different from 0 in terms of machine precision. Right? The machine can only represent numbers so small or so big before it overflows or underflows. So it's numerically, as far as the computer is concerned, it's equal to 0. So that's the p-value. Going back to the top, state the conclusion, because the p-value, okay, so I'm just stating what the p-value is there, is less than 0.05. We reject the null in favor of the alternative, H1, concluding that the mean total cigarettes smoked is different between ethnicities. Great. So we've rejected the null hypothesis. I've got this framework here, right, the Anova Hypothesis test. let me move all this hypothesis testing stuff down there. Okay. Next, we're going to check the model assumptions. And the 2 model assumptions that I ask you to check are, okay, so far we've done these top 5 parts. We've specified the hypothesis, we've plotted the data, we've calculated the test statistic, we've stated the significance level, test statistic, and p-value, and then we've stated the conclusion. So now for model assumptions, we're going to focus on these next 2, and that's about normality and equal variance. And what I would do, in fact, maybe I'll just sort of do it the way I would want you to do it, is I'd go back to the previous assignment where we did a lot of this and copy the code from there and replace the variable names. So let me go find, okay, I'm going to save this and open class 21, Anova and Pairwise comparison. I think we do all the model assumption checking in there. Okay, I'm going to go up to the very top and I'm going to scroll down a bit. Check assumptions of the test. Great. So we've got normality and equal variances. Let me take one more peek at here. So it says assess normality and check the assumptions. And if I scroll down here, I just have one big section for check assumptions. Okay, so this is easy. I'm going to take all this, I'm going to copy from class 21, everything under checking model assumptions. So I've got a plot there of the residuals, I've got a QQ plot, and I've got the formal tests of normality. Then I've got calculations of the standard deviation by group, by smoking group. I've got formal tests of the equal variances, and that should be it. Okay, so I'm going to copy all that stuff from class 21, and I'm going to put it here under checking assumptions. So I pasted it in there, I'm paging back up, and I'm ready to get going. So the Anova that I had was Anova underscore summary. So I may need to scroll up and down a little bit in order to change the variable names. All right, so first thing I've got is the residuals, and this comes from the Anova summary is the object that I have, and the residuals is an object under there. And so this is, I'm just creating a very simple data set for the called df underscore residuals. It has one variable name called res. In fact, let me run this one line of code. I don't think it ran it. There we go. And look at the structure of df res. It has one variable, res. Okay, and that's good enough because I'm just plotting a histogram and overlaying a normal curve on it. A bin width of 0.2 is not big enough for numbers of cigarettes. This is going to take a while. Let's do bin width of 10 to start. Okay. You can see that that was a very disappointing plot on the right. Let's try 10. Well, right, so this is one of those cases where it's going to be unsatisfying no matter what we do, because we have these big spikes where, like, these are all the non-smokers right here. Non-smokers are ruin it for everyone. Anyway, so there's our histogram. You can see how narrow these bars are. Maybe I need to make them a little fatter. In fact, there's values slightly less than that. Oh, that's because non-smokers from different groups will have different values down here. That makes sense. These are probably all the Caucasian non-smokers. They're the largest group. All right, let's do one more thing. Let's make the bin width 20. Let's make it 50. Okay, I can live with this. So let's zoom in on this. So we clearly have right skewed data. We knew that from before when we looked at the individual plots. Of course, the blue curve, right? See how the blue curve goes up and down chasing each of these humps? That clearly doesn't look like the red normal curve. This data is not normal. We knew that going in. I think that there's a way, geome density, there is an argument in here that you can put to change the smoothing of that blue curve. In fact, it's worth taking a minute to look at that. If we look at the help for the function geome density, and scroll down a little bit, there's this argument called adjust. And so let's go down and read the information for the argument adjust. A multiplicative bandwidth adjustment. Okay, so for example, half means use the half of the default bandwidth. So if we take adjust and set that equal to 5, for example, we will get a blue curve that's much smoother. Oh. I hate how it jumps around when I change the size of things. It's very hard to work on in a tiny window for these videos. I do that because I know that some of you might be watching this on a tablet or maybe even your phone. And if I look at my whole big laptop screen, you won't be able to see the text. Okay, I need to just wait. It's because I've resized this plot window, it's working to replot the plot. And once that finishes, then it should go back over and do the stuff I clicked on. There we go. So it did plot it, and then I had clicked on this play button, so it submitted it. And I think I clicked on it like a few times. So it's plotting it 3 times now. A way to avoid that problem is to delete the plot, clear the plots before you start resizing. All right, so let's take a look at how we have improved the smoothing. See how much smoother that blue curve is? I like that better. Anyway, it's clear that the blue curve and the red curve don't match, but I'm showing you sort of ways of improving that smooth density plot. Okay, I like what I just did there. Adjust equals 5 on the geome density line. All right, so we plotted that, and we don't need these points here, but we'll describe the plot. The plot of the residuals is very right skewed, not normal. Okay, that's my interpretation. The QQ plot, we'll also look at that. And we don't have fit C, we have the dataset Anova. And we'll run this. Ooh. So an upward curving sort of U-shaped pattern means that we have right skewed data. So that's this is extremely strong evidence that we do not have normal distribution. If we did, it would be following that blue line down there. Okay. And I can basically I can give the same interpretation over and over again. Okay, and it's probably not even worth doing the these tests here. Oops. Let's see. But let's do them for completeness. Let's look at the p-values here. They're all going to be equal to 0. One of them has a p-value smaller than what the computer can calculate accurately, so it just gives up. So all of these are very small p-values. We have rejected. Oh, and the Shapiro-Wilk won't even calculate it when you've got sample sizes that are too large. So we have very strong evidence. In fact, is that an error? If it's an error, it will stop the knitting from running. So let's comment out the Shapiro-Wilks test so it doesn't give us that error. You will probably get that same error unless you have a small subset of your data. And I'll just say the same thing I did before, that okay, a formal test out of the residuals, that's fine. I'm going to do one more thing. Under the QQ plot, let me make that window a little bit bigger. I know I'm jumping around a little bit. Here's the QQ plot. I'm going to say the QQ plot of the residuals versus the normal quantiles is very right skewed, sort of U-shaped. Okay, and then finally, the formal normality tests of the residuals rejects H naught, conclude, in favor of HA, concluding that the data are not normal. Okay, so that concludes all the normality tests. I'm going to clear my plot area. Let's check the equivariances. So we're going to calculate these summaries. I don't think I've done that already. Let me page up to grab the dataset and variable names. I can get all three right here. And I do that just so that I don't mistype things. So I've got my nisarc.sub is my dataset. My group by is the ethnicity. And I'm going to calculate my statistics for the total smoked variables, and I might have some missing values, and so I'm going to make sure that I remove the missing values before trying to calculate these statistics. Finally, let's call this summary dat, how about eth sig summary. And I'm going to print it out down here. Okay, if I've done it all correctly, then let's make sure I'm paging up a little bit. This is where it starts, so I didn't get any errors, and this is my table. Okay, so first we're looking at equivariance. And we're going to do that by looking at the standard deviation, the square root of the variance. Okay, so we're going to look at the numerical summaries, and we're going to interpret those standard deviations. And what I see is the smallest one is about 200, and the largest one is 420. So one is about twice as large as the other. That the other thing to notice is that those two standard deviations come from the two groups with the smallest sample sizes. But still, 700 and 1300 are pretty large. So these are probably pretty accurate to what the true standard deviation is. So I would say that these standard deviations do not look the same. So I think we've got some evidence here that we've got differences. Do we recall what the original plot was for the data? Let's scroll up and create that plot again. I'm getting a warning here about the function y. That's in the stat summary. You can change that to just fun. Okay, so by looking at this, it does look like let's run this one more time too. Okay, so the Asia group has 194. It does look like they've got less variability. And the one with the most, Native Americans, it's hard to tell on this plot, but apparently they do. They must have a bunch of values up here between 1,000 and 2,000 relative to the rest. So, okay, I sort of am feeling convinced that the variance between these groups are different. So I'm going to say the standard deviations appear different between groups. In particular, the Asian group has less than half the variability, the standard deviation, of the Native American group. Okay. And we can look at some formal tests. And in this case, we don't have, so we've got sigma squared 1 up to 5. And we've got, so we should put in our data set names here in our variables. Okay, so I'm just pasting down here data equals the NISARC, and I've got the total cigarettes smoked, tilde ethnicity, and this is what I'm going to put in to these tests. Okay, so I put in the response variable, the numeric variable, tilde categorical variable, comma, data equals the data set name. And I'm just going to replace that in each of these. And these are all going to reject the null. So working backwards, the Flinger test has a p-value that's equal to basically 0. Page up. The Levine test is basically equal to 0, and the Bartlett's test is basically equal to 0, the p-values. So all the p-values are basically very, very small. Because the data were not normal, we interpret see my comment down here? If normality was reasonable, then use the Bartlett test, otherwise use Levine. So I'm going to say we interpret the Levine test. The p-value is very, very, very small, less than 0.05. Therefore, we reject H0 of equal variances in favor of H1 that I think I do HA, that the variances are not equal. Okay, so we've rejected both of our model assumptions of equal variance and normality. There are a couple other model assumptions, but these are the ones that we can test. you know, our observations need to be independent, things like that. Okay, last is the post hoc tests. So let's go back to the rubric, since we've been away from there for a while, and see what we've done. We previously had completed these first 5. We just now assessed normality using the QQ-plot and Anderson-Darling, okay? And then assessed the model assumptions of equal variance. We also mentioned the standard deviations of each group, so we've done all that. Finally, we're going to proceed as though our model assumptions were met and do the pairwise comparisons. And we are recognizing that we are doing this only for pedagogical reasons, and in practice we would have stopped when we rejected our model assumptions and moved to a different test, a non-parametric test. All right, so let's do this last step. And I'm going to do the same thing that I did before. I'm going to go to the previous assignment. Let's save this file. We've done a lot of work. And go to the previous assignment. I'm going to page down, and here are the post hoc comparisons. I'm just going to copy everything that we have there. Actually, it wasn't very much. And put that into the post hoc comparisons. And let's page up to the top of there and work on our example. Okay. I don't really need some of this text here, so we're going to do some tidying up. Okay. Some of this text was for learning reasons for the last assignment. For some reason, I always keep the plotting interpretation here because it's easy to forget what the comparison arrows mean and what the blue confidence interval bars are and so on. So I'm just going to keep this paragraph here, and then we'll put in our variable information down below. I think we just need, what do we need? We need ethnicity, and we're going to need our analysis of variance object. So I'm just paging up to find the analysis of variance object, AOV summary. I'm going to page it back down, and I'm going to put that in here. So in the estimated marginal means function, we've got the Anova object, and then specs, is going to be equal to the categorical variable. And then we're going to print out the means and confidence interval, and then we're going to print out the pairwise comparison. And we have already specified that the adjustment method is Tukey, because from this list we've chosen the number 2, and that adjustment method is being put down here with how you adjust the pairwise comparison. Furthermore, when we plot this, we've also used the adjustment method there. The last thing that we need, I guess, is not smoke, but ethnicity as the label here. So there's a lot going on. I think I've got it all right. Let's run it. Some of this is left over from before. I can get rid of that stuff. Whoa, those are very different. Looks like Asians and Hispanics are not statistically different, but everyone else is. And look at how short that arrow is. We have such a large sample size that in order to be not statistically different, you've got to be basically the same. That is one problem with our project, is that we have a sample size that's too big, really, to do good statistics on. It's much nicer to have a smaller sample size. Then you can, as students, you can experience having realistically small sample sizes and seeing that there's a lot of overlap between your groups and stuff like that. But this is a real data set, so I'm happy with it. Let me page up in the console and see some of the results. Okay, so here is the first output for the estimated means. For each of the 5 groups, we have their means. So 244 is the Caucasian ethnicity. 244, that's the black dot right there. The lower and upper confidence interval spans only 8 cigarettes over a month, 240 up to 248, and that is the height of the blue bar. If we look at one that's a bit wider, because Native Americans are the smallest sample group, it has the widest error bars. So they're up at 293, that's the black dot, and their confidence interval goes from 269, the lower end of the blue bar, up to 317. Okay. Finally, the pairwise comparisons. There are 5 groups, so there should be 10 comparisons. So the first 4 lines here pair Caucasians with each of the 4 other ethnicities. Then we move on to the second ethnicity, and African Americans are paired with each of the other 3 remaining ethnicities. And then the next one is Native Americans. They are paired with the next 2, Asians and Hispanics. And then Asians is the next one, and they're paired with the last one, Hispanic. All right, if we just scroll down the p-values, we see that they're all less than 0.05, except for the very last one, Asians and Hispanics. And that's what we saw immediately in the plot. Asians and Hispanics, their red arrows overlap, which means that they are not statistically different, but all other pairs don't overlap. Wait, if you draw a horizontal line. So that is the conclusion. So let's open up the console up here. All right. Interpret the comparisons. Okay. So the way I had done this before is I had listed all the pairs. That's something that you could do. This is here, let me figure out how to. So if I were to grab this table, right, and paste it in here, this is something that you could do. You could take all the pairs, and if you remove, sorry, a little sloppy on this editor. Okay, you could do something like this. And say for each pair, let's see what's up here. Oh, it looks like I copied more. Wait a second. I think I copied and pasted a lot more than I meant to. Yes, I did. Okay. Sorry, let me just tidy up my sloppiness. Okay. So you could do something like that. Do we have a code like bulleted list or something? Edit. I don't think so. There probably is a way to make that a bulleted list, but I guess I'll just do that. Okay. So we could say, significantly different for each of these. And then not significantly different between Asians and Hispanics. You could do something like that. Alternatively, you could say all pairs of ethnicities are differ except Asian and Hispanic. Okay. So how you do that depends on what results you get. Okay. I do also recommend, because it's a nice way to summarize it, summarize the results by ordering the means and grouping pairs that do not differ. So one way to order the means very easily and get like a little table is to use the arrange function. I think we've got some numeric summaries around here. Here we go. Remember these? Alright, so let me bring this down here for a moment. Create a new code chunk. And let's just take a quick peek. So I just pressed Control Enter to run that code chunk. It put just that object down here and it printed it. So if we take that and we arrange it by the mean, now we've got it sorted by mean, right? We have the smallest mean up to the largest mean. And maybe one sort of real simple way to summarize it, since we've got our table in sort of a vertical format like this, let's delete the stuff that we don't need. Sure. Maybe we'll just delete this stuff. It takes a few seconds for me to get my keys working in the right order. Okay, so let's do a vertical version of this. That plot where we've got the bars connecting the groups that are not statistically different. It's going to be pretty easy in this case. Let's tab this over, make a little space. And over here, the two groups that were not different were the Asian and Hispanic groups. So we can I'm going to make vertical lines with the pipe character. That's the shift / character. Those two lines are grouped, and that's it. All the other groups are different from each other. So one way to do that might be to do something like that, and we just sort of realign these like that. So 1 and 2 are grouped together with that vertical line. 3 is different, 4 is different, 5 is different. And that's it. Summarize the results. All right, let's go back to the rubric and see that we've done everything. If you rejected the Anova hypothesis, perform follow-up pairwise comparisons using 2 keys on a significant difference to indicate which groups have statistically different means and summarize the results. Great, I feel pretty good about that. Let's knit this assignment and scroll through and make sure that everything looks good. So I know this is a longer video, this is a bit longer assignment, but analysis of variance is fairly involved. I am showing you how to do ANOVA carefully, as a statistician would, being very careful about checking model assumptions, at every step checking model assumptions in a few different ways. We're being very thorough. The reason I'm doing this is to protect you, and because I have seen a lot of very bad statistical work out there, which contributes actually to the replication crisis that you may have heard about in psychology and medical science and almost every other discipline where they use statistics. Because what someone might do is they might just fit the ANOVA and then do the pairwise comparison and walk away. And if they had done that in this example, because we are violating model assumptions quite strongly with our right skewed data, the conclusions that we draw may not be correct. And we would be making very bad inference if we use the conclusions that we just made for our data. But I see people do this all the time when I consult with them. So I really want you to be thorough in checking your model assumptions. All right, so let's go back here and just step through and see that we like what we've done. Okay, so we've got our hypothesis here. It's okay if you delay the hypothesis and say it below, and also give your notation below. But I've started by just looking at what are our groups and give the frequencies. That looks pretty good. We've got a plot here that shows us everything that we need. We see our right skewness. We see where the means are. That we've got very narrow confidence intervals because we have extremely large sample sizes. It's labeled appropriately. We are skipping the transforming the response. Then we've got the steps of the Anova Hypothesis test, copied from above where I talk about the mechanics of the hypothesis test. We've got the correct value here, mu5. All those means are equal to each other, significance level 0.05. We use the Anova function to conduct the hypothesis test. We have a very, very small p-value. We specify what the F statistic is and the p-value, and it is numerically not different from 0. And we conclude that because it's less than 0.05 that we reject the null in favor of the alternative to say that the number of cigarettes smoked is different between ethnicities. Of course, if you had a p-value that was larger than 0.05, you would fail to reject the null and conclude that the average number is equal between your groups. You would still check your model assumptions, but you wouldn't do the Tukey post hoc tests at the end. All right, so then we check our model assumptions. We've got a plot of our residuals where the blue curve isn't anywhere close to the red normal distribution. We've got a QQ plot, which is strongly right skewed. This curve does not follow the blue line. And we've stated our conclusions about each of those. We've done a formal test of normality and saw that all these p-values, in particular for the Anderson-Darling, is very, very small, less than 0.1 for normality tests. And so our conclusion here, the normality tests reject the null, in favor of AA. We can make one correction here. Okay, so I've corrected that, and we've also looked at the standard deviations between our groups and saw these big differences. In particular, the Asian groups had twice the standard deviation of the Native American group. And then we had some formal tests for equal variance, where we tested whether sigma squared, which is the variance, was the same between groups 1 up through group 5. And these tests, Bartlett's assumes normality, so we're not going to use that one. Levine does not assume normality, so we can use that one. We could also use Slinger, but both of these have p-values that are very, very, very small. And so because the data were not normal, we interpreted the Levine test, and it was less than 0.05, so we rejected the null hypothesis of equal variances. Then we went on to do the post hoc pairwise comparisons, and we saw that the pairwise comparisons adjusted for Tukey gave p-values that were very small except for between Asians and Hispanics, which were not different, and we gave a plot summarizing this numerically, and we also created a table that said that they were significantly different except for the last one, and finally reported the means in order of the means, and in that table summarized the results by grouping the pairs that were not different, which were the Asians and Hispanics. And that's everything. So I hope you learned a lot through this assignment. I really hope these videos are helpful. I I can't imagine that they're not. You know, I walked through the assignment in the same way that I would hope that you would walk through it with your own data. So I really hope that this is a good value for you. I know that taking this class online is not how we wished it was happening, but I still hope very much that you're getting a lot out of this class. All right, I'll see you in the next one.